Hello, welcome everybody. This is Lisa Rosenbaum from the Automotive Division of ASQ and in joint with the Quality Management Division. I want to present to you tonight's webinar, CorrectSPC, the correct use of non-Shewhart SPC in precision machining, presented by Bob Doring. And please bear with me. A little bit of housekeeping. We'll talk about a little bit about ASQ Automotive Division and Quality Management Division, tonight's seminar, and then Q&A. So everybody's phone is on mute. This session is being recorded. The session could last as long as 90 minutes. And here's where you would be able to download the slides and the video at www.asq-auto.org or www.asq-qmd.org. You can participate through the chat and with questions. Most likely we'll take those at the end. Again, I'm Lisa Rosenbaum. Automotive Chair is David Butler. A little bit on the vision and mission. ASQ is the world's leading professional association and authority on quality. And we've got our two divisions here. I'll just let you read that. And next we have Bob Doring as our speaker. And Bob has been in the quality field for over 20 years. He's currently a quality engineer for an automotive component manufacturing firm, as well as a consultant in SPC, metrology, and quality concepts training. He holds associate degrees from Lorain County Community College of Elyria, Ohio, excuse me for my lack of good diction, and the University of Akron, Ohio. A BA in Business and MBA in Systems Management from Baldwin Wallace College in Berea, Ohio. And Bob, I'm going to turn this over to you.
Okay, I'll do a couple of clicks here.
Okay, let's, there we go.
Okay, I want to welcome everybody to this seminar. I'm going to start right off going through some basics, because it's through the basics that we learn the exceptions to what we already know, and that's going to be important for today. So the first thing I want to do is define statistical process control. Providing that this lets me. Oh, it's locked up. Hang on just a second, see if we can get this going again, because it's, there we go. Statistical process control is the monitoring and reaction to a process based on statistical methodologies. So you see there, it doesn't necessarily have to be a Shewhart chart, because Shewhart charts are a subset of all statistical process control methodologies. It's virtually anything that uses statistics to help make decisions on a process. So when you look at precision machining for statistical and the statistical process control that is used with it, you go on the shop floor and you'll typically find SPC charting and machining operations that are X bar and R charts or individual moving range. Oftentimes you'll find them with incredibly compressed control limits, or you'll find capability indices that are too high, too low, or maybe bimodal distributions. But the fact is, it's precision machining, so it simply can't be that bad. So something else has to be going on, and we're going to take a look at that. First of all, I like to benchmark AIAG because they've spent a lot of time with statistical processes. And one of the things that we see in the AIAG PPAP 4th edition is what we commonly know as the capability indices. Now what's interesting about these indices is you see the familiar 133 and 167, but oftentimes people don't read beyond this. And there's more in the book that is important to read. 2.2.11.5, processes with one-sided specifications or non-normal distributions. The organization shall determine with authorized customer representative alternative acceptance criteria for processes with one-sided specifications or non-normal distributions. The problem with this is the customer representatives don't often know what to do with it either. So it's kind of a misleading direction for this, but we'll continue on. What's key about this is the note. The above mentioned acceptance criteria, which is the 133 and 167 that we saw above, assume normality and a two-sided specification with a target in the center. When this is not true, using this analysis may result in unreliable information. So if you have a distribution that is accepted distribution for the variation that you're working with, and it is neither normal or two-sided, then you have a problem using those indices. Then it continues where it says these alternative acceptance criteria could require a different type of index or some method of transformation of the data. The focus should be on understanding the reasons for non-normality. For example, is it stable over time, and managing variation. We're going to do that tonight for precision machining, but I want you to understand that what we're going to find is a non-normal distribution, and we will have to develop a different type of index that's appropriate for the distribution we're going to use. The one thing we're not going to do is a transformation because it's totally unnecessary. So when it goes to control charting on the floor, what do normally people do? Well, they grab their big X bar and R rubber stamp and they start stamping all over the floor because they believe the urban legend that an X bar and R chart will work for any distribution. Unfortunately, that's not true. Let's first go through what a normal process is. It's in control with chance variation. That is, in order for a process to be normal, it should be able to be set at the mean and will continue to randomly vary about the mean without any operator intervention. So if you're familiar with precision machining, you know that if you set a machine at a particular size and walk away from it, it's not going to stay there. And we also know why. So what kind of a process might be normal? Well, how about cutting the grass? What you do is you set the deck of the mower at a certain height, you mow through the grass, and like any quality professional, you grab your depth gauge or your caliper, go out there and start measuring the height of the grass. And what you're going to find is that the grass is going to be about the same size, some a little higher, some a little lower, randomly varied about whatever that deck setting is. More importantly, each blade of grass is independent. It has no relation to the blade of grass next to it. And that's an important thing to recognize when using these statistics. So what is in control? A process in control is in the ideal state of 100% conforming and predictable. It must remain stable over time. It must operate in a stable and consistent manner. It must be set at the proper level, somewhere within the specification. And the natural process spread must not exceed the product specified tolerance, which is a very verbose way of saying it must be capable. So what are the type of variation causes? Well, we know that there's common and special causes, and oftentimes there's debate as to what is a common to be the one defining them tonight. So a common cause is inherent in the process. It affects every part. So examples of pressure and tool wear. That's right. Special causes, they are assignable. They do not affect every part. For example, tool breakage. That's right, when a tool breaks, only those parts after the tool break are going to be affected by that cause. Another very important special cause is startup and change of operators. Startup and warm up particularly because during that period of time as the machine, the tools, the holders, everything in there is starting to come up to temperature, all kinds of changes are occurring that you have virtually no control of. So during startup, you're going to be under a special cause in and of itself. So traditional SPC expects all special causes have been eliminated. It expects the remaining variation is random, with most of the variation close to a central value. It seeks to find trends from within an otherwise random output to act upon when they occur, which are your Western electric rules, for example. So if you think about it, it's pretty much like looking out into space, trying to seek signs of life. What you're going to find typically is noise. You're going to listen to noise until you see a pattern, because a pattern shows intent. A pattern shows something is going on that was intentional. And when you see such a trend, you can take action to determine what is its origin. So really, it's more monitoring than control. Expecting random, looking for some kind of a trend. Now, if you take a look at the total variance equation, you'll see that all the variance you see is additive. And in precision machining, for example, you have this type of equation where you see the variance includes primarily tool wear, but you also have measurement error, gauge error, material, temperature, operators, and so on and so forth. Now, one of the things I want to delineate is the difference between measurement error and gauge error. Gauge error is the kind of error that you try to look at when you're doing your gauge studies, such as your gauge R&R. You want to know how much error is intrinsic in the gauge. Measurement error is when you take a perfectly good gauge and use it incorrectly, therefore generating variation that otherwise wouldn't exist. Keep that in mind because we're going to return to that a little later on. So really the total variance equation is pretty much like a fishbone in a equation format. Now nobody ever calculates it, but it's an interesting concept to keep track of when you're trying to figure out what's going on with your process. Now each of your variances can have different distributions, and that's going to be important also as you look at the effects later on of these variances on the output that you're observing. The variances that can affect your output can be additive, they can be asynchronous, that is, each participating variation can be at different levels at any time. Or you can be multimodal, such that various types of distributions, unless one variation source vastly outweighs all others, especially if excessive gauge and measurement error masks the process distributions with their normal distribution. And that's often what we see. People think they see a distribution that is normal, whereas what we're really seeing is the measurement error masking the underlying process distribution. So let's define precision machining, because there's different kinds of things that people perceive as precision machining, but there's specific ones we're going to talk about in this particular case. It's going to be a process where material is removed by a cutting surface, such as grinding, honing, turning, milling, etc. The process must be controlled in a manner that all variation, such as vibration, bearings, gauge error, all variation is statistically insignificant except tool wear. And that's important because we don't want it masking the tool wear, and it shouldn't be participating if it is precision machining. Now what happens in a precision machining situation? Well, I'm going to take the grinding operation as kind of the gold standard because of the type of tool wear that we see on there. Now what happens is as the wheel wears, each consecutive part gets a little bit bigger. It gets a little bit bigger, and a little bit bigger, and a little bit bigger. At some point in time you have to say, hey, this is too big. We have to make an adjustment or it's going to go oversized. So you make an adjustment and then you allow it to wear again. If you do this over time, what you will observe is a sawtooth curve. And this is the kind of process control that you want to have when you have tool wear. When you do this, you'll see that the diameters get larger and larger and larger, back down to another level, larger, larger, and larger, back down to another level, larger and larger, larger. Those two levels that you're adjusting between are your control limits. If you take a look at the resulting distribution, you'll see that it's not a bell curve at all. In fact, it's rectangular. And that would be the continuous uniform distribution. The sawtooth curve and precision machining is a non-normal distribution, the continuous uniform distribution. Now, if you look at it, you can see that it's very stable. And not only that, the math is incredibly easy. Do not confuse it, though, with the discrete uniform distribution. That's the type of distribution you get when you roll a die. When you roll a die, you have 6 different opportunities, but which one pops up is random each time, and it's always going to be exactly those 6. Whereas with the continuous distribution, it can be any value between A and B, and it actually comes up as a function, not random. So do not think of this as discrete uniform distribution because those are the incorrect statistics for precision machining. Often you can read this in a journal article, believe that journal articles have the most street cred. Well, you can look at this journal article called Process Control and Evaluation in the Presence of Systemic Assignable Cause by these gentlemen here in Quality Engineering. Now, they refer to it as a systemic assignable cause. That's what they call it, but as we discussed earlier, it's really not a systemic assignable cause, it's actually a common cause. But in any event, what they noticed was, and over to your right you can read this, 50 consecutive pieces are collected from a bar grinding process over a cycle and are measured for bar diameter. The data for the single cycle is presented in a table shown next to it. If you look at the chart, what they're seeing is the beginning of a sawtooth curve. So they have actually, in this journal article, identified that when a grinding wheel wears, the ODs continue to get larger. So we have that to support us. Unfortunately, they attempted to come up with calculations for control limits that were incorrect. So we give them half credit for developing the sawtooth curve, but we'll have to repair some of the work that they did as far as process control. Now, AIAG SPC 2nd edition also refers to a condition called repeating patterns. There are times when repetitive patterns are present in control charts due to known assignable causes, or common causes in this case, or causes that cannot be economically eliminated. You cannot economically eliminate tool wear. So if you can see, they've identified the sawtooth curve. Now they continue by saying when these types of repetitive patterns exist, the average chart will exhibit conditions associated with out-of-control process since there is economically influenced special cause acting on the process. Well, actually what they're saying is you're going to have a run, and a run looks like you're out of control, whereas actually you're in perfect control. And as far as economically influenced, well, you can't pay enough for a tool not to wear. So there's not much you can say. Actually, once again, tool wear is a common cause, but we'll continue. If the influence of this special cause can be shown to be predictable over time, and we do know that tool wear is predictable over time because it's a function we refer to as tool wear rate. An additional variation is acceptable to the customer, which of course we hope the customer is acceptable to toolware, because if they want precision machining, it's pretty much a part of that process, then process controls can be modified to allow it. So AIAG has identified that we can actually change process controls and modify them to allow this type of variation. Now some people say, well, you don't need to do that because regular control charts work fine thanks to the central limit theorem. The central limit theorem says that a sufficiently large number of independent random variables, each with finite mean and variance, will be approximately normally distributed. Precision machining has a sufficiently large number of data points, but are they independent? No. Actually, they're dependent because, as we said, tool wear rate is a function, so it is dependent over time. How about random? Nope, it's not random either because, again, it's a function over time. So the variables that we have are dependent and non-random. So each with a finite mean and variance, and they will not be normally distributed. The central limit theorem does not apply to precision machining output. So sometimes people say, well, that doesn't matter because CHEBYSHEV inequality will support the use. However, CHEBYSHEV inequality gives upper and lower bound for the probability of a value of random independent variable with finite variance lies within a certain distance from the variable's mean. Well, once again, we're not talking about anything random or independent, so the CHEBYSHEV inequality doesn't apply either. So here's some interesting points. The mean has no real value in controlling a process with the uniform distribution. If you looked at the distribution, it goes between A and B, and in fact, as it passes the mean, it may wave and say hi, but it has absolutely no impact whatsoever on what's going on in the process. So, running to the mean is not how you control a process with the uniform distribution. In fact, when you run to the mean, it causes over-control and over-adjustment. And if you look at TS 16949 2009 8.1.2, one of the things it tells you is basic statistical concepts such as over-adjustment shall be understood and utilized throughout the organization. So you need to understand that if you have people running to the mean, that means they are becoming the process by adjusting all the time when they don't need to. The only time you should be making an adjustment is when you are at the control limits. So we have a variety of control charts that are at our disposal. Which one would be the best? Would it be the X bar and R, the X moving range, or this new option I'd like to discuss today, the X high-low R? Now if you take a look at the X bar and R control chart, it's pretty common, everybody's familiar with it. But let's see what happens here. You take a part, you measure a diameter. You take another part, measure a diameter, and go on to each of the consecutive parts. You take those data points and calculate your average and your range. Everybody knows this is how it's done if you're using an X bar and R chart. However, I have a trick question. The trick question is, especially for machining round parts, how measurement error because you only measured one of the diameters, which doesn't actually represent the diameters that are on that part. So neither of these data points are going to provide you really any decision-making power on your process. Also, we found that the X-bar and R chart have ridiculously tight control limits when calculated for precision machining. Now, why is that? Well, it's right here. If you take a look at this, it's because they're based on the range of your sample. Problem is, consecutive parts in precision machining aren't going to have much range. In fact, what's generally detected is the within part variation, not the between part variation, and the between part variation is what you're looking for. So none of this is going to do you any good because your range is going to be pretty much zero on a precision machining operation. So X bar plus or minus A2 times 0 is X bar. That is why the control limits are ridiculously tight. There's very little variation in consecutive parts in precision machining except for your measurement error, which once again is the variation that's within that you're picking up, not between, which is what you really want. And this has nothing to do with your process variation over time. So again, you're calculating ridiculously tight control limits that have no meaning over your process. So the X-bar chart from the X-bar and R charts represents the average of an insignificant sample of measurements for a circular feature. Measuring multiple samples is a waste of time in precision machining because pretty much they're all going to be the same if they're within a very short period of time. R charts from the X-bar and R charts represent the range of measurement error, not the variation over time. So that's incorrect. And the control limits are calculating using statistics for the wrong distribution, the normal distribution, and you have a continuous uniform distribution. Now, rule of life, if you measure one diameter, you'll measure a good one, and the customer will measure a bad one. So how are you going to measure and control circular features? You measure the part and record the largest and the smallest diameters. Then you're controlling all possible diameters because by definition, they all fall within the largest and the smallest diameter. So instead of measuring one diameter, you go around the part and measure several diameters and you plot the highest and the lowest. Then all other diameters will fall in between, and as long as you have those diameters in control, not only is your process going to be in control, but you're not going to have a single diameter out of spec. So what else can you learn from largest and smallest diameter? The difference between the largest and smallest radii, by definition, is the roundness. So we can actually control not only the diameter, but the roundness by using this technique. Now, although technically the difference between the largest and smallest radii is the roundness, charting the difference between the largest and smallest diameters is less math. less opportunity for math errors, and will still exhibit the same signals because it's simply the same thing multiplied by 2. But at least this way you're going to have both charts in terms of diameters. Now what happens when you start to chart your high and the low? Well, you can see here on this chart you have the maximum sample diameter, the minimum sample diameter, and the area between them represents the roundness. The more area between them, the more the roundness is eating up your control limits and your specification. What you do is once the large maximum diameter hits the upper control limit, you adjust the process so that the smaller diameter is at the lower control limit and then allow the tool to wear again. By doing this, you have the fewest number of adjustments. The operator has the fewest number of times that they have to go to the machine, and every diameter, not just one or two that you've measured, but every diameter is in control. I mean, you ever have somebody come up to you and say, well, I'm doing an X bar and R chart and the average is in and the range is in, but one of my points is out of spec. Is that a problem? Well, in this case, you'll never have that problem. Now, what happens if you were to only measure one diameter, you'll see variation, and that's what you see here in the black. So you'll see variation that doesn't really exist. That's all measurement error. Oftentimes, people have said, you know, that is the variation that they're trying to control, but it's not even the process variation. That's simply variation from not measuring all the diameters within the part. And that provides no process information. In fact, you might use the trend chart. The control limits are based on measurement error. Has nothing to do with the process. So it's really useless. In fact, it ignores tool wear for its control limits and goes into all of the other variations which have nothing to do with it. So the trend chart, if you were ever to attempt to use it, is difficult to prepare and maintain. It's difficult to train and use, has invalid statistical basis for its control. Its control limits are based on measurement error rather than process variation, and provides little useful information to control the process anyway. So how about the X high-low R chart? What do we have there? Once again, we do the charting based on the diameters that are the largest and the smallest. You will actually have 2 points for each of your parts, and it'll look very similar to this. Now you subtract the 2, and that's your range, and your range is going to be your roundness in terms of diameter. This is what a chart looks like on a shop floor. And one of the things that's very important on these charts is you go back and you actually have to do all those things that you were taught you were supposed to do, only now they really have some meaning, which means, for example, on this one, you'll see at point 16, a point has been circled and they've identified that they have adjusted it with a offset. That explains why there was a jump between those parts. If that jump occurred and there was no offset, something else may have happened, such as the tool chipping out or something along those lines. So you would need to have this information for these charts to be specifically meaningful. Now it counts, and once you've trained your operators, they'll understand that they really need to put that information in now. Before with the charts, they were putting it in for a while, then they quit doing it because nobody was looking at it. But now when you want to analyze the variation in your chart, it becomes very important. Now, one of the things that's always a debate is what should the chart sampling frequency be? Generally, you have 2 approaches for chart sampling. One is the dartboard approach, where you say, well, we'll do it every 15 minutes. And then you have the operator whining approach, which is, oh, we don't have enough time to do all that charting. So then, okay, we'll adjust it to every 2 hours. There's really no solid basis. However, with the X high-low R chart, because you have a function, you can actually take the rate or the time that it takes to go between the lower control limit and the upper control limit and divide it by 5, and that gives you a sane sampling frequency. The problem may be that that frequency may not be frequent enough to pick up special causes such as tool wear or those types of things. In fact, one situation I had an operator set it to the lower control limit. I said, don't touch it till you get to the upper control limit. And this was in a grinding operation. It took an entire week to get to the upper control limit. So in that case, you may want to do it more than once a day in case something disturbing happens in between, so you don't have to sort out a whole day's worth of material. However, it starts to make sense because in another situation, we had a part that made that distance between the lower control limit to the upper control limit within 25 parts. So that means they had to measure every 5 parts. It seems like a lot until they see if they don't, they're going to overshoot the control limit very quickly, and then it starts to make sense and they go ahead and do it. So it's the same sampling frequency, the number of parts it takes to go from one control limit to the other, divide by 5. If you want more resolution, you can go by 7 or a little bit more, but once again, it's up to you to determine how much resolution you want from your sampling plan. So how do you calculate the control limits? Well, if you take a look at the continuous uniform distribution, if everything was perfect and you had nothing but tool wear, you always hit your control limits exactly every time, you could actually have your control limits be your spec. However, it's never really that good because remember, you have all these other variations that even though they may be statistically insignificant, they still are there and occur. So you have to have some type of a way to protect yourself from them. If you take a look at the Shewhart equivalent control limits, they use up 99.73%. However, on those further regions, there's very small frequencies. The rule of thumb control limits that we like to use for the X-high-low R chart is 75% of the specification. Guard banding to protect from the remaining sources of variances is pretty important. Now, it could very well be if you understand your process, you may find that you don't need to do 75%, 80% may be adequate. But this is where you have to understand your process in order to develop the control limits that work. Now, if you take a look at it, remember they said that the CPK and PPK don't work if you have a non-normal distribution. Well, they're correct. In this distribution, what you have is the capability calculated by the upper spec limit minus the lower spec limit divided by the upper control limit minus the lower control limit because it's a rectangle. There's no sigmas here because you have to remember that where the sigmas come from is artificial ending of a Gaussian curve that goes on to plus or minus infinity. At some point you have to stop, and they decided to stop at plus or minus 3 standard deviations. But here we know where they stop. They stop at that little A and B that we saw on the distribution, which happen to be our control limits. So if you look at the capability 133, what we're saying is that 75% of the spec will give you a 133. The problem is if you want to go any higher than that, you'll be compressing your control limits. When you compress your control limits, you have to make more and more adjustments, which means more and more operator intervention, which is not what you want to do. And there is no economic benefit for doing so. Now, sometimes there's a benefit. For example, I had a situation where the customer says the mating parts are a problem. Can you control your process tighter for a period of time to help us out? I said, well, yeah, you can. You will have to do more adjustment, but at least now you have a reason to do so. If you don't have a compelling reason, it's not to your best interest to compress your control limits. So what kind of evaluation rules do you have? Well, the key rule you're looking for is trends in the wrong direction. So for example, if you're doing an OD, it should be continually getting larger. If for some reason it starts getting smaller instead of larger, you need to take a look at the process and find out what's going on. Tool might be falling out of the holder. Something weird must be going on, and now's the time to investigate, which is why you have the chart. Occur a little operations because the roughing tool wears at a different rate than the finishing tool pressure, finish dimension. Not see a little more of a hook type of a curve. How we know the cause and you understand the cause, then you continue. If not, you need a fresh tool. From using tools in the past, you can actually set that limit at that roundness, pull that tool out, no matter how many parts you've made, and catch it before it blows. Now what I want to do is go through some case studies to show how this works out, especially in comparison to Shewhart charts. In the case study, we had 3 groups that were sent to the shop floor to collect data from CNC machining process. Each group had one person charting X bar and R, another person charting I moving range, a third charting X high-low R. A fourth person was charged with observing any changes, tool change, offsets, etc., that the others might miss because they were so focused on what they were doing. At the end of the study, the charts and their signals were compared. So group 1, we did a CNC OD, and if you take a look at the data, you can see that the data was continually getting larger on the OD. X bar and R values, the chart control limits are what you see here, and again, as we see all the time, they are incredibly tight as far as the data. Again, this is based on the range of the individual groups rather than what's happening over time. The range chart, if we're looking at this chart, definitely this process is out of control. If we look at the individuals chart, it looks just like the X bar and R chart, only because we're looking at individual calculations, the control limits are a little wider. Again though, using the rules for these charts, we have a run, we're out of the control limits, we're totally out of control. This would be disturbing for anybody who would see it who believes that this is good information. However, when we do the X high-low R chart, we can see that there's no problem at all. In fact, between the 75% control limits, we are using a very, very small amount of the roundness, which means very little of the specification is being eaten up by that roundness. This is a very good situation. And once we got to point 12, it was time to make an adjustment, which they did. In fact, they could make another further adjustment if they chose to and run for a very long time. So based on the X high-low R chart, this is a very stable process. It's been stable the entire time. It needed one adjustment, no problem whatsoever. So what's interesting is we're looking at a process that's very stable, has no problems, but if we were to use a Shewhart chart, we would think we were having a very bad situation. It gives the exact opposite of the true condition of the process. The Shewhart charts give the exact opposite of the true condition of the process. That's why they're not correct. But let's continue. Group 2, they also did a CNCOD. Now here we see a lot of random variation. According to the X-bar R chart, looks pretty good. Looks nearly in control except for a couple of points. We have one point that's a flyer. Other than that, looks pretty good. Hardly worth being concerned about. Here, one point as a flyer for the individual charts. Other than that, not much to be concerned about. However, when we take a look at the X high low R chart, you'll see that some of the diameters are actually out of spec. You also see that the roundness is eating up a great deal of the specification. That's a very disturbing situation, but in this particular case it probably could have been controlled as long as the lower diameters were adjusted upwards into the control limits. Now what we have here is evidence that not only are the parts out of spec, but the process is out of control. Whereas the Shewhart charts say they were perfectly in control. Again, the Shewhart charts showed the exact opposite of the true condition of the process. So in conclusion, precision diameters and lengths should be primarily affected by tool wear. Tool wear and associated adjustment for tool wear generates a sawtooth curve. The sawtooth curve's distribution is continuous, uniform, or rectangular distribution. The uniform distribution is non-normal, does not follow the rules of normality, such as CPK calculations or Western Electric rules for a control chart evaluation. The X-bar chart from the X-bar and R charts represents the average of a statistically insignificant sample of measurements of a circular feature or of a length. R charts from the X-bar and R charts represent the range of measurement error. Control limits are calculated using statistics for the wrong distribution, the normal distribution. The X high low R charts represent the G, D, and T characteristics of a circular feature. Think about it. You have the diameter and the zone about the diameter that you are charting. You are actually charting the G, D, and T of that feature. Can you imagine how powerful of a tool that would be and what you're going to learn from that? The R charts provide more valuable data. The X-bar and X-high-low R charts, such as tool wear rate. You can do a linear regression on either the high line or the low line for that tool wear, and you can calculate a tool wear rate that's almost good down to the nanometer per part. They use the correct uniform distribution for precision machining. The X-high-low R charts can also be expanded to control taper. I didn't go into a lot of these other things because we only had a short time to spend together, but we do have the ability to control taper by using multiple X-high-low charting. Here's another interesting point, and it's critical, and even when I did the case studies, they found the same particular problem. Automated tool wear compensation is not statistical process control. In fact, it is an algorithm for compensation becomes a process because it's actually doing what a person would do if they were trying to run to the mean. But now you have the machine trying to do the same thing. So what happens is you lose the benefits of SPC because the constant adjustment masks the information such as tool wear rate and roundness. Now, it would be nice if that compensation was tracked so that you could determine what that was, but that's generally not available in the process. So really, automated tool wear compensation is an algorithm for over-control. That's all it does. So in conclusion, the total information is given by the observed distribution, once again attributed to Dr. Walter Shewhart, and that's what we want to use when we're controlling precision machining, is the observed distribution of the continuous uniform distribution, not the normal distribution. Now, if you have any questions, here's my email. If we don't get around to them today, or if you come up with questions later on, please feel free to email me. I'll be more than happy to assist you either in trying to apply this concept, or if you have any questions concerning the application of this process.
Bob,
Yes.
there's a number of questions that came in on the chat.
Okay, let me see if I can open this
I
up.
can read them off to you.
Okay. Okay.
Are you able to see any of them?
Let me open it up and see what we got here. Well, downloads of the present. Well, yes. Okay. I have to go back up a few here, I guess.
And
That's
then,
the only one I see.
okay. I'll just start. One of the early questions was statistically significant. Okay, and my screen just refreshed. Statistically significant compared to what?
Well, just in general, when you have one, as far as the variation, you want to be statistically insignificant because you don't want variation from bearing wear or any of these other things to mask what's going on with the tool wear. Again, tool wear is key. That's what you want to see. And if you have bad bearings, if you have bad loose ways, if you have situation chucks are loose or out of control, you're not doing precision machining. Those things all have to be in control and in good shape before you can actually do this and get down to where all you're seeing is the tool wear rate. As far as your sampling, like I say, if you measure one diameter out of an infinite number of diameter, its significance is 1 out of infinity, which is nearly 0. So that's why when you do the high and low, you've actually captured all the values, which is extremely significant. You've gone from 1 out of infinity to every value. So that's why it's a far more powerful tool.
Another question is the example shown, and they're referring to the 50-point samples, use spec limits as the reaction points, so to speak, so what was meant that they didn't calculate the control limits properly?
They might not have seen it. It's actually they were, for the X-high-low R chart, we use 75% of the specification as the control limits.
Okay.
Now, again, sometimes you need to adjust that depending on your process, but that's a good starting point.
Then another question, the mean is defined as the value of a distribution that equally divides the area under the distribution. So the uniform distribution, in quotes, does have a mean.
It has a mean, but we don't use it for anything. It has, the only thing of value as far as decision making in the uniform distribution is A and B, which are your two control limits.
Okay. Since the measurements are dependent, have you looked at EWMA control charts?
Yes, but it is still not as powerful as this one because of the ability to control all diameters with this one. And this is actually far simpler than the EWMA. But yeah, that's one of the examples we use. And again, it has a sampling issue that this doesn't have.
Then another comment, for clarity, measurements should read data. So, you know, because you're measuring, but you're collecting the data on the measurements. What can we use as proof of attendance? Okay, that I got. Proof of attendance for everybody that's attended. An email will be sent out with your RU units either this evening or tomorrow. I think it goes out tomorrow automatically. So the control limits are not determined from the common cause variation, but rather set as a function of the spec limits?
Yes, because that is the common cause. What happens is you have to have, if you take a look at the distribution has A and B. Where is the variation going to be? It's going to be where you adjust between A and B. So that is your control limits. There's no other calculations. Your variation will be based on where you set those control limits. And we simply use 75% of the specification because we need to accommodate some of the other variances that may be there on occasion and protect yourself also from special causes that might come in. But in this particular case, the cause actually is adjusted between A and B, and that's what you need to focus on in that distribution is A and B. Where does it come from? It comes from the 2 points that you adjust between. The variation that occurs after that is whatever happens, and it actually has no impact on the calculation.
Here's another question. Is there software to make such a chart?
Yes, there is, and if they email me, I can give you some examples of the charting software that's out there that's available. I don't have it handy with me right now, but I can send that out to you. Some of the big charting methods out there do have that, or can do it with a little bit of assistance.
Have another comment. Bear with me. Makes a lot of sense. Also, so with exceptionally long wear or trending, such as a laser cut, for example, but where strength of laser degrades, I'm assuming then that a traditional Shewhart with appropriate sample size, if not normal but random, would be an appropriate approach. The high-low makes much more sense for those distributions which have definite trends for sure. Thank you.
Yeah, absolutely. And I'm not really sure. I've dealt with some laser machining, and laser machining, you know, it has its own specific issues. That's why I tried to focus this on cutting methodologies, because I know for sure the tool wear applies to that. But in fact, this type of charting methodology probably has other uses that I haven't personally been able to verify, such as plating. When you have plating chemistry distribution, you know, you start out with a lot of chemicals in your plating bath, and then they drag out over a period of time, and then you need to make an add, and so on and so forth. You end up with this type of a variation also. But I just personally haven't applied it to that I could use it as an example, just as a potential for people that may be in that to take a look at. In that case, it wouldn't be high and low, because when you do your titration, you pretty much get a value. So some people have also looked at electrical drift. There's a variety of things that this may apply, because they don't have that random variation, but a function that's adjusted.
Okay, here's another question. I work in precision stamping industry. Seems that CorrectSPC would apply in stamping also. Please give me your thoughts.
Well, it does, but it's a little bit different, because you don't generally adjust a stamping die. So generally you get one cycle. So, but what's important to understand about this is that, you know, you've probably been beat up before by people saying, well, your process needs to be centered, and of course it can't be, because you have to start with it either small or large, depending on whether you're doing an ID or OD, to allow the tool to wear. So you still have a tool wear issue. You may have a little more variation based on material that participates, and sometimes that can mask what's going on, especially because your tool wear now isn't over an adjustable period of a week or a day or an hour, but months. But in the long run, you do have the same type of thing, where if you were to track your dimensions, and you'd have to track the exact same locations. You can't be looking at different areas, because that'd be no different than if you were measuring a circular feature in different areas and being masked by taper. You don't want to do that. You want to measure in the same location all the time. And you'd have the same issue there. You had to measure the same location, and you should be able to see over a long period of time that tool wear, and it should be predicting when to pull that die out when it's hit the end of its life and due for change, if you don't have other things such as edge condition that precedes that.
Okay, here's another one. You mentioned once tool wear is a special cause, but it's truly a common cause, correct?
You know, I'm sorry. If I did, I meant it is a common cause because it affects every part. Other people have identified it as either a systemic special cause or you know, they try to identify it, but you can't remove it. You can't remove it. So it's common, it affects every part, and it's intrinsic in the process, so it's a common cause.
Okay, here's another one. Loss function seeks least variation about nominal based on cost of deviation from nominal. In that respect, automated tool wear adjustment could be desired. It seems tracking the compensation over time against the theoretical compensation could be useful. Comments?
Well, that's, yeah, in order for it to be of any value, because, you know, it's really doing the same thing as a person constantly running to the mean. They're going to totally lose track of what's going on with the tool wear rate because they have become the process rather than the process, which is tool wear. So whenever a person becomes a process, that's not really good. You want to pull the person out of the process as much as possible and let the actual machine be the process. It really depends.
They're saying the automated tool wear adjustment.
Yeah, that's right. And that's what it's doing. It's doing the same thing. It's constantly adjusting based on the previous part. So it's doing exactly the same thing as a person running to the mean. Now you need to take a look at, is it really, if you look at the need of that type of adjustment, and I do in my plant, we have a grinding process because there's so much variation of the blanks going into it that we need to do that. And I'm still struggling with, okay, what can I do with this kind of a process, because I can't see anything that's going on because of this constant adjustment. But in the situations where we're able to see the tool wear rate and not adjust it that way, we know a lot more about the process. The engineers know more about the process. They can see when the machine's not working right. They can see when the tools aren't as good as they used to be. And you can't see it because it's all messed with adjustments on that. But it creates more of a problem than an answer.
So therefore you should be doing regularly scheduled, or?
I wouldn't use automated tool wear adjustment unless I absolutely needed to for some particular reason, because like I say, it masks important information that will help you use your tools longer and understand what condition your process is in, and understand how well your tools are working. I mean, all this information is gone, totally gone, if that's what you're using. In fact, if you're using automated tool adjustment, there's no sense SPCing it. It's not going to tell you because it's totally over controlled to begin with.
Here's a question clarifying the 50-point question from before. The 50-point question was trying to ask, what did you mean when you said they calculated the limits wrong? Does that make sense?
Well, the only, I'm trying to think back where that was. The only thing that's calculated incorrectly is if you're trying to calculate control limits using Shewhart charts on precision machining. You can calculate them, but they are not, they're for a different distribution and a different process, and they're not and we've gone through and statistically shown that they're not applicable.
Okay.
So the thing to do is to start at 75% of the specification and work from there.
And if the I'll reach out to this person and see if we can get clarification, and we'll get you to answer it offline.
Okay.
Another question: how to compute process capability for processes with one-sided specs? The example given was two-sided.
Well, that's probably going to be a different seminar. Well, I'll tell you what I do though. Well, no, I don't. It takes too long. But I will say what I normally do is I use curve fitting because when you have a unilateral tolerance, especially if it's up against a physical limit such as roundness, flatness, those types of things where you have a limit of 0, I generally do curve fitting, find out what curve best fits it, because the closer you get to that physical limit, the less normal it's going to be. It's going to stop at that limit. And if you try to use the Gaussian curve or normal distribution calculations, they extend beyond that, and that's not physically possible. Whereas if you get into some of the other distributions, such as the beta or Weibull, they actually stop at that distribution and are a much better model of that variation. And then I compare those to the specification. Now, how well does a model distribution of that data best fit between the specification? And then on the other hand, if you have a lower spec with no limit up at the top, that's a very difficult calculation, because the one thing I do not use, and people often use, is either the CPU or CPL. And the problem with that is it's using the wrong model, and I don't recommend that. It's using the normal distribution, using half of it, and I don't recommend that. But that's probably a longer.
If they have more questions, they can email you.
Absolutely, absolutely.
For capability calculations, do you use all data points? Any data points you don't use for it? Any tips or suggestions and rationale you recommend?
Well, the beauty of this distribution is the points that you use are your control limits. So, and the other beauty of that is you don't have to recalculate, because it doesn't change. So you have, for example, a 133 is using 75% of your tolerance as your control limits. You don't, as long as your data falls within the control limits, you've met that. That is your goal. And there may be some exceptions where an individual didn't catch it in time, and or a tool broke. But as we know, those are special causes, and you adjust for that, and you usually don't include them anyway. So the long-term process capability is the control limits in comparison to the spec. That's it. There's really nothing else. And that goes back to the calculations for the continuous uniform distribution.
We've got lots of questions still coming in. I have another one. I think what you have described is not a form of SPC, but rather EPC, engineering process control.
Well, I would, you can call it something else, but in my mind it's statistical process control, because we are using statistics, we're using the correct distribution to make decisions on the control of the process. So it basically speaking, statistics, controlling the process, that's SPC.
Okay. And we can take that.
You can call it anything else you want, but right. I wouldn't say that it's not SPC, because it is.
Okay. Is this applicable to wire-bound process, e.g. capillary wear?
I'm not sure. Maybe. You'd have to really analyze the variation that comes out of that type of a process.
Okay,
I mean, if it has a function similar to tool wear, perhaps so.
would be a little different, man. It depends. I'm thinking in terms of my lab equipment.
Well, I'm always looking for opportunities that might be different from precision machining where this would apply. I just haven't had an opportunity to go in, look at the data, look at the process, make sure that the process is doing what we expect, and collect the data and show that it works. So, I mean, it's something to consider. And if what you see is this type of thing, which is the key, is the sawtooth curve. That's the key, where you have a variation over time and an adjustment, because that is how you get the continuous uniform distribution, which is how this is all hinged together. So if you have that kind of variation, then this is probably going to be an underpinning of the type of control that you would want to use. You certainly have, if it's similar to this, there would be no use for a normal distribution.
Here's another question. Sometimes I try to reaction limits versus control limits, just to differentiate control limits as being calculated, and reaction limits might, for example, be 75% of the spec. An out of control situation might be when there is a significantly faster or slower rate of movement or a significant change in roundness. Are there similar rules for the high-low chart beyond making an adjustment when you hit a limit?
Well, primarily that's all you're looking for, is an adjustment, unless you have a situation where the tool breaks. That's your special cause. You have to replace the tool. So, I mean, I'm not one to quibble over the name. I call it control limit because those are the two limits that I'm controlling the process between. That's the two limits. That's the A and the B. Those are the two limits that I'm adjusting between. Those are the points of control where I actually have the operator go in and react with the process. So I have no problem calling it a control limit, but you know, other people can feel comfortable calling them whatever they wish, as long as essentially you're doing it correctly. But I wouldn't say just because something is calculated it's a control limit. I don't think there's any reason to believe that calculation has to be there, especially if it's the incorrect one for the distribution.
Here's a question, again, back to referencing another. So are you saying auto-compensating in machining is not a good idea?
Well, I am. That doesn't mean that it doesn't have its place. Like I said, I have a process in my plant where at this point in time they have to do it in order to get the product to come out anywhere near, and we're talking microns. But in general, I believe it's not a good thing because you're losing incredibly powerful information by having the machine do what you wouldn't want an operator to do, which is sit there and constantly adjust it. Remember, with this process, it only works if the operator only adjusts it when it hits a control limit and adjusts it to the other control limit. If they're constantly adjusting it, you can't use this approach, because now you probably will have random variation about the mean. That's one of the things that I found when I went into area. If I see a control chart with random variation about the mean, I know that that operator is over controlling it, And like we said, and it goes even back to TS, you don't want over control. That's not the process, that's the person becoming the process. You don't want that. You're trying to eliminate that along with some of the other bad things that we find. So yeah, I generally don't recommend it if I can avoid it. Now what I'd like to see is the people that are doing the auto compensation figure out a better way of doing it so that you can actually collect this information. There may be some hope at that point, but right now they're generating noise.
So as long as your auto compensation is repeatable and documented that this is the process in order to do your compensation, is that okay?
Well, all I'm saying is if you're using auto compensation in order to control your process, it is the process. And what's even scarier is most people don't know what the algorithm is. You know, like, what is it doing? Well, yeah. You ought to know what it's doing because it is your process. It is, the output is whatever it thinks it's doing. And I've even talked to some places that make the machines that are using the auto compensation, and some of those guys don't even know what the algorithm is because it comes from a different location. It's not the place where they're actually trying to set up the machines for a case. You cannot really, it becomes the process is all I'm saying. And so things like wheel wear, if you're doing auto compensation on a grinder, wheel wear, when to make it adjust any type of operator intervention to the wheel itself, you won't know that. You just have to kind of guess because it's all masked by this constant adjustment.
Here's a question. Are 3 to 5 measurements across a sample diameter, or even for sphere, reasonable to determine the max and min diameters?
It depends on how much roundness you have. I prefer at least 4. I would do at least 4. I found when doing a CMM that if you do 8 points, which would be close to 4 diameters, you don't get much better than that by doing 10 or 12. So what's going to happen is your measurement error from doing that is going to be very, very, very small. It's going to be whatever extends beyond that from your sampling, and that's going to be very small, especially compared to doing 1. So the more you do to some degree is better, but you're going to have a limit as to the benefit. And you can probably even detect that from doing several studies.
Here's another one. Some special causes cannot be removed, as you say, but may be compensated for, as you do by adjusting the process. EPC is just that, adjusting the process to compensate for identified special causes. That might just be a comment.
Well, like I say, I mean, you know, there's no real point in quibbling over the terminology as long as the application is correct.
Right, and I think this, you know, maybe we'll take this one offline and I'll send you the contact, because I think it might be an interesting point to be made. I don't have enough to give my evaluation on it. Did you give another question? Did you give a relative value for what percentage of the total variation toll wear should be for this to be effective? Would that be a percentage? Would that percentage be the basis for how much of the specification you allow before adjustment?
Well, you have to know your process. If your process has, outside of tool wear, a lot of variation, you're going to have much tighter control limits than 75%. The point is, if you actually have precision machining and you actually have all of those variations in control, you know, your bearings are in control, in fact, what happens is you can actually see these things getting worse from this charting methodology, and we've actually the engineers in my plant are tickled to death because they can see this now where they weren't able to before. They can see by suddenly a particular machine has much more roundness than the similar machines. So, well, how is this happening? Then that's when they find out that they have problems with their chucking, they have problems with their bearings, or whatever type of repairs need to be made. And, you know, again, this isn't a rubber stamp type of thing. This is going to take knowledge of the process, which includes, you know, getting the engineers involved that are familiar with the machines and the materials to understand what kind of variation you can expect. And you do that probably the best by doing a capability study, which, by the way, you do the exact same way. When I do a capability study, I start doing 100% of the parts, but I do them by measuring the high and the low, not by single points. And even when I'm calculating capability studies for a customer, that's what I'm going to do, is I'm going to do a high and low. I'm going to say this is where we adjust it, and this is what the process looks like, because that is a true evaluation of what the process variation is, not some single calculated index, because that doesn't really tell you anything about what that process is going to do over time.
We still have quite a few more questions and only about 10 minutes left. One person wanted more thoughts on one-sided tolerance, but I think we're going to skip over that. We'll get back to that, or you can
have them email me, because I do have a paper that I put together on one-sided tolerances.
Okay,
I can send
I'll
to them.
put that together. Do we use, okay, by definition, your CPK is basically 1.33 or whatever you want them to be based on the selected control limits?
Well, it just happens to be. Remember, I don't call it CPK, because CPK is a function of centering. It's also a function of the normal distribution. I simply call it, and I'm just making this so that everybody understands, because if you look at Boss' book on capability, there's what, 150 different indexes out there to take a look at. But this particular index is simply the trying to find out where your distribution fits in the specification. It just so happens your distribution is, by design, your upper control limit minus your lower control limit. And if it's 75%, then it's 133. If it's 50%, then it ends up being 2 or whatever. But the problem is, you're going to, if you compress your control limits to get a higher capability, then you have more operator intervention, more adjustments with very little economic benefit to you or your customer. If their specs are real and correct, that means that if your parts fall within a specification, they work. If they're not real, you have a different issue, but you may be able to help them out by controlling your process better.
Do we use SPC for common causes or special causes?
Well, traditional Shewhart charts expects common causes and tries to eliminate special causes when they occur. In this particular case, what we're doing is controlling the common cause. We aren't just watching it like you would do with a Shewhart chart. Shewhart chart just watches it like noise and waits for a pattern to occur. We have a pattern. We're just trying to control the pattern in an area between the specifications. So it's a little different thought process than what they're doing with a Shewhart chart. And that's why we call it a non-Shewhart methodology.
I would use an X bar and R with a sample size of 1 and the range being the high and low reading of the part measured. What do you think?
Well, an X bar indicates using an average, and I don't calculate any averages with this because there's no point. The average doesn't do anything for the distribution that we're looking at. So I just simply take one part, measure around it, get the high and low, and then measure consecutive parts and watch the tool wear effect on them and make adjustments accordingly. So yeah, I don't use averages at all. There's no real benefit by them.
Yeah, because he's saying with a sample size of 1, so you can't
Yeah.
really do it average if you get.
And I've already gone through why the individual moving range doesn't work.
Yeah.
Because you're not controlling all the diameters.
How frequent should be the review of control limits for high-low charts?
You do it once.
Okay.
Because it's constant. You can look at it all you want, but it's a constant. So there's nothing to review. It's a totally different. It's a different concept. It's controlling the variation, whereas in Shewhart, it's observing the variation. So they recalculate it to see if the observation has changed any. But here, there's no change. You're constantly adjusting between those two. So it's a constant. It's whatever you set it at. It's 133 if it's 75%. If you take a look at the calculation, it's a constant.
Okay, here's some more on over control is adding variation, not minimizing it, correct? That's what you were saying.
Well, it does, because especially what happens with over control in machining, that means that the operator is messing with the machine more than they need to be. In fact, when I've implemented this, I've actually reduced the number of operator interventions. Sometimes they were intervening every 15 minutes, and then we get it down to maybe twice a day because there was no point. So why have the operator intervening in the machine if they don't need to? That is adding variation. It doesn't need to be there. Plus, again, you don't want people to be your process. You want the machine to be a process. And that variation, the tool wear variation is going to occur anyway. Why add more variation on top of that? Just observe the variation that the machine is trying to do. Only adjust it when it's time for it to be adjusted. And that's what you want as far as a controlled process.
Yeah, I had an anecdotal story, not on the machines, but quality went up when they didn't allow the engineers to tweak the powertrains anymore. True story. Don't know how long ago. But if the auto compensation just tweaks the offset by your known tool wear rate, not based on measuring previous parts, couldn't you flatten the sawtooth?
Oh, it will flatten. But what I'm afraid of is it's not, first of all, most of the auto compensation isn't looking at the high and low, right? It's only going to be looking at one diameter. So its decisions may be overcompensating just based on the measurement error. I don't know. And then it's going to make an adjustment even though you're not at a control limit, right? It's just going to constantly try to run to the mean. So all of these things just means that it becomes the source of variation on top of the tool wear, which is always there. And the idea is to pull away all the variation so that only the tool wear is there, and you only make adjustments when you need to. So it's a really auto compensation. A lot of people stand back and say, "Oh, this is great." But my point is, it's not great, and you really need to understand what it's doing, because it may not be doing you any favors. It's actually destroying information.
I hate to say it, we're at 7:28. There were just a couple more. One was a comment. Some reasons one would review the control limits, spec changes, customer complaints, new process, concern of leaving money on the table, change in measurement capabilities. And then another comment, I see danger in allowing a goalpost approach to specifications rather than minimizing variation about the mean.
Well, again, if you compress the control limits, you increase the operator intervention. So that's the danger I'm talking about, and you need to balance that variation with the variation of, if they want to call goalpost, it's identified statistically why we use that.
And then, let's see if I can get this. All right, it worked. So just a quick mention. I'm going to send the questions off to the presenter, to Bob, and he can answer some offline. And you should be able to download the presentation and slides at either www.asq-auto.org or www.asq-qmd.org. And we'll be posting up the webinar after the event. Any questions? I believe I'll have my email available, asqautowebinar@gmail.com. I'll try and get that on the email that gets sent out if you have any questions, or you can email the QMD email, and Doug will be happy to get back with you, and we'll get your answers, questions answered. Thank you very much. Thank you, Bob. I really appreciate it. And I look forward to the next webinar. I'll send out a communication. Thanks all.